Imagine for a moment you're overseeing the construction of something truly immense, a structure where failure just isn't an option. We're talking about a bridge designed to carry thousands of vehicles daily, maybe a pipeline snaking across continents, or the very foundations of a towering skyscraper. What's the unseen, rigorous process that ensures every single connection, every single weld isn't just strong, but absolutely fit for the immense, often unseen job it has to do? Welcome to the Deep Dive, where we take your articles, your research, and your notes, and we distill the most important nuggets of knowledge. It's your shortcut to being truly well-informed, with surprising facts and hopefully just enough humor to keep you hooked. Today, we're diving deep into the often overlooked yet utterly critical world of welding procedure qualification. You've given us some excellent source material, and our mission is to unpack how welding specifications are rigorously tested and approved, guaranteeing they meet the absolute highest standards for safety and performance. We're going to uncover the layers behind how engineers ensure a weld is not just good enough, but truly fit for purpose. So let's unpack this. Why is this entire process so foundational to engineering?
Well, what's fascinating here is that without this detailed, proven process, you'd essentially be relying on guesswork, right? Welding procedure qualification is absolutely essential because it establishes a repeatable, a validated method for creating welds. It's how we scientifically confirm that a specific welding approach will consistently produce joints with the precise mechanical properties required, things like strength, ductility, or even toughness. And, crucially, that they'll be free from defects, capable of withstanding the immense demands of their environment. It's all about creating confidence and predictability in every joint right from the start.
Okay, and I understand the bedrock of that controlled welding process is something called a Welding Procedure Specification, or WPS. What exactly is that, and why is it so incredibly crucial?
That's right. The WPS is the absolute core. Think of it as the master recipe, maybe for a bridge, not a cake.
Right.
It's a highly detailed written instruction set that outlines every single welding condition that must be rigorously followed during fabrication. Its true power lies in its purpose. It's designed to guarantee that every welded joint is not only free from defects, but also possesses the precise mechanical properties like the right strength, ductility, toughness to withstand its environment.
So it eliminates guesswork.
Exactly. It's the blueprint that eliminates guesswork, ensuring laboratory-proven safety translates into every weld made in the real world.
So who needs to be intimately familiar with this incredibly precise document? Is it just for the welders themselves, or is there a broader audience involved?
Well, while it's primarily a shop floor document, directly instructing welders on how to perform a weld, it's equally critical for welding inspectors.
Okay.
They must be thoroughly familiar with the WPS to ensure welders are actually adhering to every specified requirement. The why behind this is vital. Production welds made strictly according to these carefully tested and defined conditions should consistently possess similar reliable properties.
Making them fit for purpose.
Precisely. Making them truly fit for their intended use. It's the assurance that what works once works every time.
So if the WPS is this master recipe, how do we know that recipe will consistently produce a strong, reliable weld? That's where the real proof comes in, isn't it? It needs to be qualified.
Yes.
How does that rigorous journey to qualification actually work?
That's precisely where the robust testing comes in. A welding procedure is typically qualified by making a dedicated test weld. This is done to demonstrate unequivocally that the properties of the finished joint meet these stringent requirements specified by the application standard and the client.
So it's a validation step.
It's a journey that demands unwavering precision, yeah. Each step a critical checkpoint, culminating in the ultimate proof of a weld's integrity. It begins with the welding engineer drafting a preliminary welding procedure specification, or PWPS.
Okay, PWPS.
Specifically for a test coupon. This is the initial recipe for the trial weld, you could say. Then, a welder, diligently following that PWPS, creates the actual test coupon. During this crucial stage, a welding inspector meticulously records all the welding conditions used. These are referred to as the as-run conditions.
As-run.
Got it. And often, an independent examiner or a third-party inspector will monitor the entire qualification process for added impartiality and credibility.
So it's far beyond just a quick visual check, then. There's a lot more that goes into evaluating the integrity of that test weld.
Absolutely, indeed. Once the test weld is complete, it undergoes rigorous testing. First up is non-destructive testing, or NDT.
NDT.
Yeah, this includes visual inspection to spot obvious flaws, along with magnetic particle testing, MT, or penetrant testing, PT, for surface defects, and often radiography, RT, or ultrasonic testing, UT, to peer inside the weld for any internal flaws. And that's only half the story.
Only half, okay.
The coupon then moves to destructive testing.
Ah, this sounds serious.
It is. This is where the coupon is literally taken apart and subjected to tests like tensile tests, bend tests, and macro tests to evaluate its mechanical properties and internal structure.
Wow.
Think of it as a stress test to the absolute extreme. Depending on the material and the specific application standard, additional tests like hardness, impact, or even corrosion tests might be required.
To ensure it meets every requirement.
Every single one. It's a comprehensive interrogation of the weld's integrity.
That's a staggering amount of testing. So after all that meticulous examination, literally pulling it apart, what's the ultimate certification that emerges from this entire process? What's the piece of paper?
That leads us to the Welding Procedure Qualification Record, or WPQR.
WPQR, okay.
This is the official document that summarizes the entire qualification process. It contains all the crucial details, the exact as-run welding conditions used to make the test weld, the results of all the non-destructive tests, and the results of all the destructive tests. Crucially, the WPQR also details the specific welding conditions that are allowed for future production welding.
The allowed range.
Exactly. Right. And if a third-party inspector was involved, they would sign the WPQR, certifying it as a true and accurate record of the test. It's not just about proving a good weld once, but establishing a reliable pathway to consistently good welds.
That WPQR sounds like the ultimate gold standard, essentially proving that you can consistently achieve the desired weld properties. It's the documented proof.
It absolutely is. Now, it's worth noting that while qualifying a WPS usually involves making a specific test weld, for some applications, welding standards do allow alternative methods. Just briefly.
Okay.
This could include qualification by adopting a standard welding procedure that has already been tested and documented by others.
Piggybacking on previous work?
Sorta, yeah. Or even qualification based on extensive previous welding experience, where weld joints have been repeatedly made and proven to have suitable properties through their service record.
Interesting. But the test weld is the main way.
But the dedicated test weld method is the most common and generally the most robust way to achieve this qualification.
That makes a lot of sense. So once you have this qualified WPQR, how does the welding engineer actually translate that into clear, actionable instructions for the production line? How do they ensure that what's proven in the lab translates precisely to every single joint on, say, a massive bridge or a critical pipeline?
That's where the relationship between the WPQR and the production WPS becomes really clear. The welding engineer uses that validated WPQR to write the specific qualified WPSs for the various production weld joints that need to be made. The critical point here is what's called the qualification range.
Right, you mentioned that.
The production welding conditions must remain strictly within the range allowed by that WPQR. This is where the concept of welding variables comes in, categorized by both European and American welding standards.
Variables. Okay, let's break that down.
These variables typically break down into essential, non-essential, and sometimes additional variables. An essential variable is any variable that significantly affects the mechanical properties of the weldment, like its strength and ductility.
So, the really important stuff.
Absolutely. What this means is, if you change an essential variable beyond the specified limits from the qualified WPQR, the WPS must be requalified.
Start over.
Pretty much. This is the incredible precision demanded not just by welders, but by the very science of metallurgy. A tiny shift here can mean the difference between a structure that stands for a century and one that fails prematurely.
So an essential variable is something you really can't mess with without starting over. What about a non-essential variable? Are those less important?
Not less important, exactly, but they don't significantly affect the fundamental mechanical properties.
Okay.
Non-essential variables still must be specified on a WPS, but if you change them, you don't need to requalify the entire procedure. You just need to write a new WPS to reflect the updated conditions.
A documentation change, but not a retest.
Correct. And European standards also introduce additional variables, sometimes called supplementary essential variables, in ASME standards, which specifically affect properties like toughness or hardness, adding another layer of control for certain applications.
Right. Toughness and hardness.
Yep.
Okay. So what does this all mean for someone directly on the shop floor? Like, if I'm a welder, what are some of these essential variables that I absolutely need to monitor and adhere to? Give us some practical examples.
Excellent question. For someone on the shop floor, understanding these essential variables is paramount because they directly govern the qualification range. According to European welding standards, some typical essential variables include, first, The welding process itself. There's no range here. The exact process qualified must be used in production, period.
No wiggle room.
None. Second, post-weld heat treatment, or PWHT. If your test joint was treated with PWHT, you only qualify for production joints that also receive PWHT. If it was tested as welded, you only qualify as welded production joints. You can't mix and match.
Makes sense. Keep conditions consistent.
Exactly. Third, the parent material type. Qualification generally only allows materials with the same material group number, which signifies materials with very similar chemical compositions and mechanical behaviors. You can't just switch to a different type of steel, for example. Got it. What else?
Next, welding consumables. Production consumables typically must have the same European designation as those used in the test, meaning they're essentially the same chemical and performance family. The material thickness is also an essential variable. The test weld doesn't qualify all thicknesses, but a carefully defined range around the test piece's dimension.
There's a limit above and below.
Yes. For instance, it might be something like 0.7 times the test thickness up to 2 times the test thickness for a single run weld, but the specific range depends on the standard and details. Go outside that and you're in unproven territory. The type of current is also critical. AC only qualifies AC, DC polarity cannot be changed, and pulsed current only qualifies pulsed.
So stick to the electrical settings precisely.
Precisely. Additionally, the preheat temperature used for the test sets the minimum allowed preheat temperature for production. You can go hotter, but not colder.
Minimum preheat, okay. Conversely, the highest inner pass temperature reached during the test, that's the temperature between weld runs, is the maximum allowed for production. You can't let it get hotter than that.
Maximum inner pass.
Right. Yeah. And finally, heat input, which we mentioned is often an additional variable when impact or hardness requirements apply, has specific tight margins. For instance, the max heat input might be only 25% above the test value if toughness is critical, or the minimum heat input might be only 25% below if hardness is the concern. Too much or too little heat, and you compromise those critical characteristics.
So it's not like a bake-off where you just slap on some extra frosting to cover a mistake, is it? If a welder accidentally deviates from these conditions, what's the consequence? Is it an automatic fail, or are there ways to recover?
It's definitely not like that, no. If a welder uses conditions outside the qualified WPS range, there are serious implications because the weld may not have the required properties for its intended purpose.
Which could be catastrophic.
Potentially, yes. There are generally two options. Either you make another test weld using conditions similar to the affected production weld and subject it to the same rigorous tests to prove its properties. That can be time-consuming and expensive. Or, more commonly, you remove the affected joint entirely.
Cut it out.
Cut it out, yes. And re-weld it strictly in accordance with the designated WPS. It emphasizes the absolute necessity of sticking to the qualified procedure because the stakes are incredibly high.
That makes the stakes remarkably clear. It also highlights the global consensus around these practices. Can you tell us about the key standards that govern all this procedure qualification and ensure this worldwide consistency?
Indeed. There's broad agreement on this. The principal European standards are the EN ISO 150-614 series, specifically Part 1 for arc and gas welding of steels and arc welding of nickel, and Part 2 for arc welding of aluminum.
Okay, EN ISO 150-614.
On the American side, you have ASME Section IX for pressurized systems like vessels and pipework,
ASME 9,
and AWS D1.1 for structural welding of steels, and AWS D1.2 for structural welding of aluminum.
AWS D1.1, D1.2. Got it.
These standards are comprehensive. They detail precisely how a welded test piece must be made, how it must be tested, what welding details need to be included in the WPS, and crucially, the exact range of production welding allowed by a particular qualification test weld. They define the rules of the game. It's also worth noting that the BSEN ISO 15614 standard has 2 levels. Level 1 is based on the requirements of ASME Section IX, while Level 2 has higher testing requirements.
Level 2 is tougher.
Yes, more stringent testing. A procedure test qualified to Level 2 automatically qualifies for Level 1 requirements, but not the other way around.
Okay.
And if no level is specified in a contract, the requirements of Level 2 always apply, so it defaults to the higher standard.
Good to know.
And importantly, approval for a WPS is generally valid in workshops or sites that are under the same technical and quality control of the original manufacturer, reinforcing the consistency in application.
It's fascinating just how much detail goes into one of these documents, proving its validity at every single step. So when you actually look at a WPS document, what kind of information is contained within it? What makes it such a comprehensive blueprint?
A WPS is incredibly comprehensive. detailing almost every facet of the welding operation. It includes detailed information about the parent material.
The stuff being welded.
Right. Its type, thickness, diameter if it's a pipe, and surface condition. It specifies the welding process itself, the type, equipment parameters like amps, volts, travel speed. It details the welding consumables, their type, diameter, brand, classification, and even how they should be heat treated or stored, keeping rods dry, that sort of thing.
Storage matters too.
Absolutely. Beyond materials, it covers joint design, like the edge preparation, the root gap, root face, and any jigging or tacking needed to hold things in place. It dictates the welding position, whether it's in the shop or out on site, at specific positions like flat, horizontal, or overhead, along with any weather precautions if you're welding outdoors.
Can't weld in the rain, I guess.
Generally not advisable without proper protection, no. Finally, it outlines any thermal heat treatments required, such as preheat temperatures we discussed, or post-weld heat treatments like stress relieving to relax the joint after welding.
Wow, that covers everything.
Pretty much. So the purpose of a WPS, to recap, is multifaceted. Achieve specific properties, ensure freedom from defects, enforce quality control, standardize methods and costs, control schedules, form a record, and meet contract requirements. It's a complete, legally binding instruction manual for making a perfect weld every time.
So if you ever look at a welded structure, be it a bridge, a building, or a pipeline, you now have a much deeper appreciation for the unseen work, the rigorous testing that goes into ensuring its integrity.
Absolutely.
Yeah.
That's the core takeaway, I think. Welding procedure qualification isn't just bureaucracy. It's a critical engineering process. It pre-validates the integrity and performance of a weld before it's even made in production. It's about building trust and confidence into every single joint, providing the absolute assurance that a structure will perform precisely as designed, often for decades to come.
And why should you, our listener, care about all this?
Well, whether you're reviewing project specifications, managing a manufacturing team, or just intensely curious about how complex structures are built and maintained, understanding WPS qualification gives you invaluable insight into fundamental quality assurance in manufacturing and construction. It's the invisible shield protecting our infrastructure, really.
That's a great way to put it. And as you think about all this precision and validation, consider this. How might advancements in technology, perhaps in advanced sensing, real-time feedback systems, or even machine learning and AI, how might these continue to refine or even revolutionize these traditional rigorous qualification processes in the future while still maintaining the same unwavering high standards of safety and performance that we rely on every day? Something to think about.